Okay, so let's remember where we are. We're talking about the Radon transform. Right, and so we have some function on R3, in the Schwartz class on R3, and then we define the Radon transform. So R f of t comma gamma, where t is in R, and then gamma is in S2, right? So gamma is on the sphere, and we define it to be right. So you have this vector, you have this unit vector, and then you have some length t, right? And we define the Radon transform at t comma gamma to be the integral of our function over the plane that has normal vector gamma and is distance t from the origin. Okay, right. So you take this t gamma vector here, and then you look at the plane for which gamma is the normal vector, right? And then you integrate the function over that plane. Okay, so you basically integrate the function over the plane, and that's the Radon transform at t comma gamma. Okay, and we also sort of wrote this out more explicitly as the integral of f of t gamma plus u1 e1 plus u2 e2 du1 du2, where over R2, where gamma, E1, and E2 are an orthonormal basis of R3. Okay, right. So we have our gamma, right, and then we've got two vectors that are orthonormal, that with it form an orthonormal basis, and then we let u1 and u2 be these coordinates, and then you just integrate over all linear combinations of e1 and e2 plus d gamma. Okay. Right. So, and we also agree with u as this u1 e1 plus u2 e2. So that was just a notation. Okay. Okay. So okay. So we are going to need a notion of the Schwartz class. So so we say if f is a continuous function on R cross S2 that's infinitely differentiable in T, and the supremum of the absolute value of T of K times the derivative of f in T at any point, if the supremum over all T and all gamma is finite, so if for all K and L, we have that these things are finite, then we say that f is in the Schwartz class for R cross S squared. Okay, so what this is, you just look at it, what it's saying is that it's in the Schwartz class in the first variable, right? If you look at it, right, you're taking multiples, polynomials in T, you're multiplying the derivatives of the function, right? It's in Schwartz class in the first variable overall uniformly in gamma, right? So overall gamma, that's you've got a bound that works for all gamma. Okay, so it's in the Schwartz class in T, uniformly in gamma. Okay, so now, now we can state the important, the sort of central lemma in the theory of the Radon transform, which is this thing called the Fourier Slice Theorem. The Fourier Slice, or the Fourier Projection Theorem. Fourier Slice or Fourier Projection Theorem. Okay. And it says the following, that if you start off with a function, if you start, coming to a good point, we're doing the central thing in the theory of the Radon transform, central result in the theory of Radon transform, the Fourier Slice Theorem. Okay. So if you have a function in the Schwartz class, then the Radon transform of it is in the Schwartz class for each gamma. And this is the important part. The Fourier transform of the Radon transform in the first variable. So this hat indicates the Fourier transform in the first variable. Turns out to be the Fourier transform of f. Okay, this hat indicates the Fourier transform in R3. Okay, so this is the Fourier transform in R3, right? Because f is a function on R3. Your Radon transform in terms of S is a function on R1. So we take the Fourier transform, the one variable Fourier transform in the first variable here at S comma gamma, and that turns out to be the same thing as the three-dimensional the Fourier transform in R3 of the function at S times gamma. Okay, so pictorially, what that's saying is that right, if you fix a gamma, right? So you fix your direction here, right? And then you do the Radon transform of the function, right? So that what that's doing is basically collapsing, right? Collapsing the integrating the function and into a one variable thing, right? Right. And then you take the Fourier transform along that direction. That's the same thing as if you took the original function, and then took its Fourier transform, and then it just evaluated it at S gamma. Okay, so this is pretty cool, and you see, I hope, why it's called the Fourier Slice Theorem or the projection theorem. You're projecting the function down onto this one variable line, okay, and then taking its one variable Fourier transform. Okay, so this is cool. The main part of the theorem is this identity here, which is just a calculation. So it's proof of the identity. It's a calculation. You say, okay, well, let's take that. Right. So by definition, right, that's the you're going to take the Radon transform. So you take the integral of f along p t gamma, right, and then e to the negative 2 pi I s dot t, s times t, pt. Right, so it's just by definition. Okay, and using the notation that we put up before, well, that's f of t gamma plus u1 p1 plus u2 e2 du1 du2. Then we have this e to the negative 2 pi as t dt. Over R2. Okay, which will rewrite again using u as u1 e1 plus u2 e2. We'll rewrite that as f of t gamma plus u du e to the negative 2 pi I s t dt. That's not that important. Okay. And then at this point we pull a trick. We rewrite the t. So we note that, well, we can rewrite the t as gamma dot t gamma plus u. Right? Because remember, u is in the plane that's perpendicular to gamma, right? U is in the plane, gamma is the normal vector to that plane, right? So when we take the dot product, this thing vanishes and we just get gamma dot gamma times t. Well, gamma dot gamma is 1. Right. Okay. So we rewrite this. I'm going to do some bad word work and just write this here. Gamma dot t gamma plus u. Du dt. Okay, and then, so, right, this thing here is t gamma plus u1 e1 plus u2 e2. And we do a rotation, so rotate t e1 e2 to just the standard vectors, standard basis. To the standard basis vectors. And that changes this into f of x e to the negative 2 pi I s gamma dot x dx. Right, which is just f hat f hat of s gamma. Okay. So it's just a calculation. Okay, so that's the Fourier slice or Fourier projection theorem. Okay. Okay. Yeah, kind of.
Does an analogous theorem hold in Rn? Because I would expect it to. Or
Yes.
okay.
Yes.
Cool.
Yes. Yeah. Yeah. There are such things for like for Rn, and in fact for the K-plane Radon transforms that are integrals over things that are codimension, whatever.
Yes.
Yeah.
Yes.
Yeah.
But like the idea of
Slicing
a
down.
Fourier transform in Rn is really just down some line, dependent on. What I'm trying to say is something like this. What you drew here, you have a line going through the origin. It's really just a one-dimensional Fourier transform through the origin once we fix the right C or something like this.
Yes.
Okay.
Yes.
Does this theorem work only if you start in one dimension and drop to even dimension, or does it work even if you?
No, I'm pretty sure it works in whatever dimension. Yeah. 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 If you're interested, look at the work for the k-plane Radon transform is done by this guy named Keinert. So you can look up. He has a paper where he basically redoes the theory for the k-plane transform. Okay. So k-plane. I'm sorry. The Fourier Slice Theorem. Immediate corollary is that we can reinterpret the Radon transform as simply the inverse Fourier transform of this function, right? So that is you take the three-dimensional Fourier transform along this line, but you invert it with respect to S, right? And that will recover the original Radon transform, right? Because the Fourier transform in the first dimension, in the first variable of the Radon transform is this. Just invert both sides with respect to the first variable.
Mm-hmm.
Okay. So immediately we get that RFT gamma is just going to be the inverse Fourier transform of this thing on the right. Okay, but keep in mind that this is the three-dimensional Fourier transform. Okay. Okay, and that's going to be that fact is sort of sort of like a alternate view of the Radon transform is going to be very useful. Okay. Another corollary that we get is that if f and g are in the Schwartz class and the Radon transforms are equal, then the original functions must have been equal. Okay. And the proof is pretty straightforward. You say, well, look, if the Radon transforms are equal, then the Radon transform of the difference is going to be 0, right? But that tells you that the Fourier transform of the difference at every S gamma is going to be 0. Right? Right? But that means that the Fourier transform is 0, right? The Fourier transform at every point, at every frequency is 0, which means that the function, the difference must be 0. You invert both sides. Okay. So yeah, so you have this uniqueness result. Okay. The next thing we want to do is answer the question: can we get back to the original function from the Radon transform of the function? Right? Like how do you go backwards? And there's that will the formula is called the filtered backprojection inversion formula. Okay. And that involves something called the dual Radon transform. So right. So remember, like f we started off with a function on R3, and then the Radon transform is a function on R cross S2. Okay, so the dual Radon transform will go from functions on R cross S2 and return as functions on R3. Okay. So for f, a function on R cross S2, we define the dual Radon transform of f at a point x, right? So for x in R3, we define this to be the integral of f at x dot gamma gamma d sigma gamma over S2. Okay. So we take our function, we integrate over all directions, and evaluate our function at x dot gamma comma gamma. Okay, that may seem kind of like why would you do that? But if you think about it, in the case of the Radon transform, right? What are we doing? The Radon transform evaluated at x dot gamma comma gamma, right? Well, that's the integral of your function over the plane x dot gamma comma gamma, right? That's the integral of your function over the plane x dot gamma comma gamma, right? In other words, right? You've got your gamma, right? You've got some point x, right? And then you're integrating over the plane x dot gamma comma gamma, right? So what's that? That's going to be the plane at distance x dot gamma, x dot gamma from the origin, and with normal vector gamma, right? So you're integrating over the plane, right? What plane is this? This is the plane that is normal, the plane through x, with normal vector gamma. Okay, and so when you look at this thing, right? If we're taking the right, if we're taking right over S2, well, what are we doing? We're taking right. This says take the integrals over all such planes, right? Take the integrals over all planes. So what you're doing is you're fixing a point, right? If you take the dual Radon of the Radon transform, what it means is that you're going to integrate the function over all planes passing through that point, right? Right. Each of these things, right? Each of these guys. This is right the integral over the plane through gamma with normal vector gamma, and then you're letting gamma rotate over the sphere. Okay. So it's you're basically averaging the function over all planes that pass through that point. Okay, and so you think that maybe that gets you somewhat back, somewhat close to your original function. In fact, we can. So this thing here is called the backprojection operator. And the inversion formula involves putting what's called a filter on the back projection operator. So here it is. For f in the Schwartz class 3, then if we take the projection operator, but then take the Laplacian of the projection operator, we recover our function with some constant. Okay, so okay, and this follows from the recharacterization of the Radon transform that we used earlier. So recall what we got out of the Fourier Slice Theorem was that we can rewrite the Radon transform as the one-dimensional inversion, Fourier inversion of the three-dimensional Fourier transform. Right. So now we'll use the dual Radon transform on we'll use the dual Radon transform on that. R star RF T gamma is the integral over all directions of the function evaluated at x dot gamma. Okay, right. So just applying the dual Radon transform, and then we just differentiate. So then, the Laplacian of that is going to be, again, you're allowed to differentiate under the integral sign, and you just pull out you pull out a negative for pi squared s squared. Okay, SS e to 2 pi I x dot gamma s squared ds d sigma. Right. When we differentiate, we're going to pull off gamma 1 squared s squared, and then the sum of those will be just the norm of gamma, which is 1, times s squared. Okay, and then it's again a calculation. We split this into two parts, the integral from 0 to infinity plus the integral from negative infinity to 0. Right, and then it's just calculus from here on. So you do a change of variables, and you end up with the same. You end up with the same thing. So you end up with negative 8 pi squared of s squared from 0 to infinity f at s gamma e to 2 pi I right? And then then we just use this is the spherical integration on R3. So we can change this into negative 8 pi squared integral of f hat x e to the 2 pi I. I'm sorry, sigma e to the 2 pi I x dot sigma d sigma. Not sigma, d xc d xc. Over R3. Okay, and that this of course is the inverse Fourier transform. This is the inversion formula, right? So you end up with negative 8 pi squared f of x as desired. Okay. So it's just a calculation that comes out of the Fourier Slice theorems. Comes out of the Fourier Slice theorem. Okay. Okay. So that's the filter back projection formula to recover the function from its Radon transform. And this is this is basically what is used in CAT scans, right? Right. You have the Radon transform. The CAT scan gives you it's the X-ray transform, but in any case, some sort of Radon transform, and you're wondering like how do I get back to the original thing? Well, you use the filter back projection inversion formula to get back. Yeah, question.
Just a few words about. Well, I just don't know if I understand why this is working. Why do we need to take a Laplacian to get the information we want?
Again, you're asking for some sort of intuition.
Yeah,
right?
That's okay. Yeah. I thought we were going to try to build R star such that loosely, like R star R is the identity, but it's not quite. And I guess it's not quite in this way. Right.
So it's rather an average of all the it's an average of all the integrals over the planes through that point.
Yeah, totally.
Right. But why taking the Laplacian of it would give you back would fix the blurriness. So if you look at just a back projection operator, what you see is that it's this kind of like blurry average of the actual thing, and then you use the Laplacian, and somehow that sharpens the image. Okay, because you using a derivative gives you information about edges, kind of, right?
Yeah.
So if you I don't know if that helps.
I see what you mean. So the back transform is kind of an average at all these points.
Yeah.
And the Laplacian is saying how fast is this average changing in each of the three directions. But its derivative is squared, which is kind of okay. Yeah.
Yeah, I'm afraid I don't have anything.
No, that's helpful though. Thank you.
But no, it's kind of cool to see if you look at the, because people are always trying to do things along these lines, right? In the area of medical imaging, right? You want to find something where you can get the minimal amount of radiation and yet the sharpest image, right? And so at least it was a topic of a lot of research to try I expect it probably is, it still is, to try and come up with algorithms that would do this with minimal, yeah. Yeah.
Is the reason we choose R star to be what it is it like the adjoint of R in some?
Yeah. So I didn't mention it. So that's an exercise, but yeah, basically, like if you have V1 being the Schwartz class functions on R3, and you create you define the usual inner product, right? F against G bar, and then you define V2 to be S on R1 cross S2 with the similar inner product. Then then they're adjoint to each other. Yeah. So RFG is the same thing as RFG in the second one is the same thing as F. I'm sorry. In the first one. Yeah. So that's I think that's in the exercises. Yeah, I've been to conferences where people bring up their algorithms and show. It's kind of an odd thing because it's more sort of like we try it out and it looks like it works better, right? They'll give some sort of empirical evidence for a lot of it's sort of like they'll give empirical evidence that their method is able to to recover the function, recover the original function effectively. Yeah.
Yeah, this is like, so if we have R star on, like from infinite dimensional linear algebra, we know that that's a positive operator and it has all these nice properties. Do any of them carry over here? Does it mean, and of course its inverse should also be fairly nice, so does that mean that the Laplacian is the inverse of some sort of positive operator? Does it get nice properties from that?
I don't know. I don't know. Let me sort of dig through. Yeah, I'm sorry. I don't know. Yeah. Okay. Okay, we've got 5 minutes left. Maybe. Maybe that's a good place to stop, actually. Yeah. Well, I mean, so I think. Yeah. So what we're doing next is going on into Fourier analysis on finite abelian groups. So I think, yeah, and that's basically lays the groundwork for the last chapter where we'll do the proof of Dirichlet's theorem on arithmetic progressions. Okay, so the flavor is going to change somewhat, but yeah, I think let's just stop there. Let's just stop there. We'll start with that next time.
Is that chapter 7?
Chapter 7. Yeah. Maybe this is of interest to you. I don't know. I don't know. I forget if this is in the book or not. But in RD, you define something called a fractional Laplacian. A fractional Laplacian. As negative Laplacian to the alpha of f of x equals the t by c dot x dc times 2 pi absolute value of c to the alpha over RD. Right. So this matches up with the Laplacian, if sorry, this should be a 2 alpha. Sorry. Okay. So if alpha is 1, then you get your normal
Right.
your normal Laplacian, and then the reconstruction formula is then you use dual Radon transform, but you hit it with the fractional Laplacian with the Laplacian d to the minus 1 over 2, and then there's some constant.
Is this in general, like in RD?
Yeah, this is in RD. So in
Ah.
RD. And again, this is one of those things where the odd and even cases are very different.
I see.
Why so? Because
Because of 2. Because if it's odd, then you get an integer.
I see.
Right,
And this
and
is
if
why they
it's-
choose. Okay.
And if it's even, then
They choose to cover the R3 case.
Yeah.
It's easy.
Yeah.
Why? So it's like we're taking what would be the inversion formula and we're inserting this term into it. Why is the term? Is it a typo that it's not 2 pi I norm c, or should it be this way? And what is?
It's interesting.
Maybe it shouldn't be this way.
The book has exactly that.
It's interesting. What is this? Because it looks similar to the term we add when we want a derivative.
Yeah, and it should.
But it's not quite right because the term that would give us a derivative is multiplied by I, or am I
Well, it looks similar to what we're looking at when we're constructing the heat kernel.
Oh.
Sorry, the Fourier transform of Poisson kernel.
The Fourier
When
transform.
we're solving the
Well,
heat
maybe
equation.
that's for this negative, right?
Mhm.
Oh, because if it's 2 to the alpha, then
Yeah. Right.
Ah.
Right. Because if there's an I there, you get to the alpha, you're going to get -1 to the alpha.
We look at I to the 2 alpha, which is equal to -1 to the alpha.
Yeah.
Yes.
Yeah. That's I guess that's fine.
Ah. Okay. So it is just a yeah.
Yeah.
it's pretty interesting.
Yeah.